For this lesson, we're going to be looking at a specific type of problem that can often be solved using a system of linear equations. And that is sometimes it's referred to as a percentage problem, sometimes it's a mixture problem. And that's based on how the values are given to you in your question. A couple of things that I want to remind you of before we get started looking at some examples. You can represent a percentage as a fraction or a decimal, and obviously you can work between these things. Sometimes you'll be given values, often as percentages, and it may be more convenient for you to represent them as a decimal or as a fraction, or sometimes it might even be useful to represent them as a reduced fraction once you've converted this. So in this case, for example, 25 over 100 can be reduced to the fraction 1 over 4. So that's also something you might want to keep in mind. When you're doing these types of problems, keep in mind the wording of the question. Use that wording of the question to help you figure out what your variables are going to be. And the biggest clue in the wording of the question is going to be what is it that you're actually trying to find, because that at least steers you in the direction of what you should be looking for. And then read the question 2 or 3 times, circle things, underline things, try to give yourself a chance to figure out what it is that you could make some meaningful variables from. And make sure your units are consistent. Usually the questions will have consistent units to start with, but don't get thrown if you see things with units that don't quite match up. It is your responsibility to make sure that those units are consistent before you go to any depth with the question. So, having said that, let's go ahead and take a look at our first example. All right, so in this case, we have a mixture question where we're trying to, or where we have a type of granola that's made of 30% fruit, which means the other 70% is made up of something that's not fruit, oats or nuts or something like that. We have a second type of granola that's made up of 15% fruit. Now we want to mix these two types of granolas together to make 600 grams of granola that is 21% fruit. Okay, so this is what I want my final mass. 600 grams is how much I want to create for my final mass. And this is my final mixture. This is my final mix percentage. 21% fruit. So imagine if I started with this, I've got a big bin of 30% fruit granola. If I just took out 600 grams of that, then my mixture would be 30%. If I used only 600 grams of 15% fruit, well, that would be all 15% fruit mixture, so my final amount would be 15%. So it's only by doing a combination of some 30% plus some 15% that I'm going to end up somewhere in between. Now it's not exactly the middle, but it's somewhere between 15 and 30%. So I'm adding a certain amount of the 30% mixture and I'm adding a certain amount of the 15%, and to get a total amount of 21%. So I think that leads us pretty well to our variables. So let x be the mass of 30% mixture. And I'm going to let y be the mass of 21% mixture. So let's see, if x is the mass of the 30% mixture and y is the mass, sorry, I've written this incorrectly. Y is not the mass of 21% mixture, y is the mass of 15% mixture. So I've got some 30%, that's x, some 15%, that's y. I'm going to add those together to create 600 grams total. That's the final mass. So my first equation falls out of that very readily. The mass of 30% mixture plus the mass of 15% mixture has to add up together to be the final mass. Equation number 1, and that's a nice simple equation to work with. Now we have to figure out We know we want our final mixture to be 21% fruit. So this one's a little bit tougher to imagine. If 21% of the final mixture is fruit, then what is the mass of fruit in the final mixture? Well, if the final mixture weighs or has a mass of 600 grams, and 21% of it is fruit, then 0.21 times 600, this would be the mass of fruit in the final mixture. It's a pretty awful looking word, fruit, there. Okay. 21, the 0.21, that came from 21%. And as I said in our first slide, you can represent a percentage as a decimal. Now, if that's the case, if that's my final mass of fruit, well, how much did mixture number 1, the 30% mixture, how much fruit did that contribute? Well, it contributed 0.30 multiplied by the mass of the 30% mixture, which is X, plus 0.15 multiplied by the mass of the 15% mixture is Y. And again, just to remind you, the reason the 0.30 is here because that's from the 30%, and this one is from the 15%. And the X and the Y and the 600, that is a mass, and that one is a mass, and this one is a mass. So we've got a mass of each, and then the percentage of fruit of each tells us essentially the mass of the fruit. So this is the mass of the fruit from the 30% mixture. This is the mass of the fruit from the 15% mixture. And when you add up those two masses, you end up with the mass of the fruit in the 21% mixture. So that is our equation number 2. Now this equation is fine. We could work with this as it is. But these numbers, 0.30, 0.15, 0.21, they're a little bit on the awkward side, and it might actually be useful to work with a friendlier looking equation. And I've got each of these decimals is to each of these decimal numbers is to 2 decimal places. The way I can get rid of that is I can actually take equation 2 and just multiply the whole equation, left side and right side, by 100. 0.30 times 100 shifts the decimal over twice, and I end up with 30x. 0.15 becomes 15y equals, and 0.21 times 600 just becomes 21 times 600. And I'm going to call that equation 3. You may not be bothered. You may just think, oh, I can work with the decimals. I'm fine with that. And if you are, that's okay. No one's saying you have to do this. Now it turns out now that I've done this multiplication, I realize, oh, I can make this simpler still. And when I talk about making things simple, really your focus on making things simple is on the coefficients of the x and the y. There's not a great deal you can do about if you've got any constants. They're just going to be what they turn out to be. But for the coefficients of x and y, you might realize that is there a number that goes into all of these? And if you think about that, well, 30 and 15 goes into both of them, but 15 doesn't go into 21 over here. What about 15 going into 600? Does that work? And it turns out that, well, 15 multiplied by 4 is 60. So 15 actually does go into 600. So I can actually simplify this whole equation. If I divide both sides, left and right, if I divide everything by 15, I actually get a pretty nice result here. The equation I get from this is 30x divided by 15 is just going to give me 2x, plus 15y divided by 15 is just going to give me y. And now, I said that 15 goes into 60 4 times. So that would mean this 21 is just going to stay the same. So if 60 divided by 15 is 4, then 600 divided by 15 would be equal to 40. And now I'm going to call this equation number, oh, I guess I should maybe simplify this. 2x plus y is equal to, let's see, 2 times 40 is 80, so 20 times 40 is 800. And then I've got 1 times 40 is 40. So this looks like this is 840. And that's equation number 4. If you did not see this divided by 15, don't feel bad. You can still solve this. It just means that the numbers you're dealing with are worse. In this case, I've reduced this to the point where there's a pretty good chance I'm going to be able to carry on with this, not have to worry about a calculator. The numbers are going to be fairly reasonable. So take a look at equation 1, take a look at equation 2. This actually looks pretty well set up to do elimination. I'm going to eliminate the y's, and I want to do 2x minus x. So I'm going to put equation number 1 underneath here. So this is x plus y equals 600. And then I'm going to take equation number 4 minus equation number 1, using good communication to represent everything. 2x minus x is simply equal to x, plus y, and then subtract another positive y is equal to 0. 840 minus 600 is equal to 240. So now I have my x value. That's the mass of the 30% mixture. Let's find the mass of the 15% mixture. So I'm going to sub x equals 240 into, and let's look back at the equations we've got. Which one of these equations, 1, 2, 3, 4, is going to be best suited to find y? And pretty obviously, equation 1 is pretty much perfectly set up for this. So I'm going to sub that into equation number 1. And that becomes, I'll just keep it on the screen there. That becomes, instead of x plus y, that becomes 240 plus y is equal to 600. From that, I end up with y equals 600 minus 240. As I take the positive 240 over to the right side, it becomes negative 240. And y ends up being equal to 360. Those masses, 240 and 360, are going to be measured in grams because we did our final mass in grams. I mentioned earlier, you got to make sure your units are consistent. In this case, there was really only one unit we had here, which was grams. What mass of each type of granola should be mixed? So now we have our answer. X represents the 30% mixture, so therefore mix. So I want X is 240 grams of the 30% mixture. I'm not going to use the word mixture. I'm just going to say mix 240 grams of the 30% and how much? 360 grams of the, what's the other one? 15%. Just going to clean this up a little bit. 240 grams. Need to make sure that actually looks like the right numbers. 240 grams. Okay, so there's our first mixture example. Moving on. A chemistry teacher is trying to make 10 liters. So in this case, we're not dealing with a mass, we're dealing with a volume, liters. 10 liters of 42% sulfuric acid solution. So I'm not going to get into the actual chemistry of this, but 42% sulfuric acid solution, that means that 58% of this would just be water. It's kind of like saying pure sulfuric acid mixed in with some water to dilute it. So that's what we want to produce. The solutions that we're starting with are a 30% solution and a 50% solution. And this actually, although this is a lot of questions that we do in math are very contrived, this actually is something that happens in the chemistry lab. From companies, you receive you'll receive different amounts, but of course you may be doing an experiment that requires something like a 42% solution, but you might have a big jug of 30% solution and a big jug of 50% solution, and it's up to you to do this calculation and to figure out how much you need to mix it together to produce this. So this is actually a moderately realistic problem. How many liters of each solution must be mixed? So this one is very much like our previous problem. Let X represent the volume of, let's see, we have 30% solution. And we're going to let Y represent the volume of 50% solution. I mix those two volumes together, X plus Y, and I'm trying to produce 10 liters. So that's my first equation. I want to combine X amount of 50% solution. Now, in the previous example, if you've been doing these, following these in order, in the previous example, I wrote that as 0.50. So I wrote this 0.50x for 50%, and that'd be plus 0. Have I got them backwards? I do have them backwards. The x goes with the 30%. 0.30x plus 0.50y is equal to, and we want to produce a 42% solution of 10 liters. So this is the percentage of sulfuric acid, this is the volume. Percentage, volume, percentage, volume. This is a much more subtle way, but when we talk about making sure our units work, making sure our units are consistent, this is a sort of another way of looking at consistent unit, which is this is a percentage of sulfuric acid and a volume. Percentage times a volume, percentage times a volume. At least the way I'm building these things is the same every time. So in that previous example, and I'm just going to go ahead straight to that, which is I multiplied everything by 100 to eliminate the percentages and the decimals, equals 42 times 10. And you might go ahead and actually resolve that. So I'm going to say 30x plus 50y equals, because that one's pretty easy to get to. But now you take a look at this, and actually everything ends with a 0, or I could have recognized the 10 here. I can divide everything by 10. So if I divide everything by 10, I end up with a simpler equation, 3x plus 5y equals 42. And then we ask ourselves, is there an even simpler form of this? But unfortunately there's not. We can't divide by anything that they have in common with each other. So that's just going to be my equation 2. Now, from there, I need to combine these two equations somehow. So what do I want to match up? Well, again, and I think I've shown this in some of the questions I'm doing, elimination just works so well. We've got these, they're already in the same form. Equation number 1 here is so easy to manipulate. So I could easily just multiply equation number 1 by 3. So if I turned this into a 3, the way I would do that, that would let me eliminate the x from here. So I'm going to go ahead and do that. And the way I'm going to do that is I'm going to say I'm going to take equation number 1 and multiply it by 3. And that gives me 3x plus 3y equals 30. I took this equation and I multiplied this by 3. I'm just going to go ahead and equation number 1 times 3. 3x plus 3y equals 30. And that's what came down here. Now I'm going to take equation number 2. Oh, I guess I better label this. Equation 1 times 3 becomes equation 3. And then we're going to do equation 2 minus equation 3. 3x minus 3x is 0. 5y minus 3y is 2y. 42 minus 30 is equal to 12. And then to solve that, divide both sides by 2. And I end up with y is equal to 6. Now I'm going to sub that into equation 2, equation 3, or equation 1. Equation 1 is awfully tempting for that. Let's make sure we keep it on the screen. So now I sub y equals 6 into equation number 1. And so that becomes x plus, and instead of y, I'm going to put 6 equals 10. So x is equal to 10 minus 6. X equals x is equal to 4. Let's do a quick check. So now I'm saying x is equal to 4. That's my 30% mixture. And my 50% mixture, I want more of the 50% than I do of the 30%. Well, I'm trying to make 42%. So if we imagine we've got 30% mixture here and 50% mixture here, well, if I did half and half, that would make a 40% mixture in the middle. But I don't want a 40% mixture. I actually want this 42% mixture. So which one should I have? Which one should I be closer to? Which one should I have more of? Well, to get closer to the 50%, I need stronger 50%, and I need less of the 30%. So it makes sense that I would have more of this one, and I would have less of this one. And I take a look. This is my 30% mixture, and this one is my 50% mixture, and I have more of this, and I have less of this. So my answer actually does make sense. Therefore, and I'm going to use 4 liters of, or let's say at 4 liters at 30% and 6 liters at 50%. Okay, that one was very similar to our previous one. Let's take a look at our last one, see if it's any different. Okay, for this one, a candy store is preparing a mixture of chocolate raisins and chocolate peanuts. The raisins sell for $2.22 per kilogram, and the peanuts sell for $1.75 per kilogram. How much of each type must be mixed to make 20 kilograms, that's my total, of a mixture that will sell for, and this is not per kilogram, this is my total price. Okay, so this doesn't look the same as the ones we just did, yet there's some commonalities here. We're interested in the mass of raisins and the mass of peanuts, so that one's easy. Let x be, and don't feel you have to use x and y all the time. You know what? For that reason alone, I'm going to change this. We're not going to use x and y. We're going to say let r be mass of raisins, and we're going to let, not so creative here, let p be the mass of the peanuts. Okay, that's pretty awful. I have to rewrite that. Sorry, can't put up with it. A little bit better. Okay, so if I add together my mass of raisins and I add to that my mass of peanuts, what do I end up with for my total mass? That is equal to 20 kilograms. And once again, thankfully, we end up with a very straightforward first equation. Now our second equation is where things get interesting. The raisins sell for $22.22 per kilogram, and I have R kilograms of them. So that means 222 times R, that is not the mass, R is the mass, and 222 is the cost per unit mass. So these two things together, that is the cost, or let's say that's the total cost of raisins. And then we add to that plus 175 multiplied by P, because that is the total of, I better say the word cost, I don't want to take a shortcut there. That one is the total cost of peanuts and the total cost of my raisins plus the total cost of my peanuts must add up to be the total cost of the mixture. And that's it. We've got our second equation. Now, I might, again, make this equation a little bit nicer to work with. It's up to you. If I multiply this out by 100, this number on the end is going to end up being really large. Or if I leave it this way, then I'm going to be working with decimals. It's up to you, either or. In this case, again, just to vary things a bit, I used R and P. I'm changing variables, so why not keep changing things? So I'm going to do this one by substitution, and I'm just going to leave this equation in its not very nice looking form. Partially that's because there isn't really a much better looking form for this one, and the other reason is we haven't done one like this yet. So what do I want to get rid of? Do I want to get rid of R or P? It's really very arbitrary. So I'm going to take this equation and I'm going to rewrite it as, well, since P is next to the equal sign, that's a good enough reason for me. So P is equal to 20 minus R. And I'm going to call that equation 3. And then I'm going to substitute equation number 3 into equation number 2. So what's that going to look like? Substitute equation 3 into equation 2. Equation 2, wherever I have a P, I'm going to replace it with, so wherever I have a P in this equation, I'm going to replace it with the equivalent value, which is 20 minus R. So I end up with 2.22 R plus 1.75, but instead of P, I'm going to put 20 minus R, and that is all equal to 41. Okay, so now 2.22 R, I have to expand out this bracket, 1.75 times 20, 1.75 times negative R. The first one of those, just a little bit of mental arithmetic, 1.75 times 2 is 3.5, so times 20 would be equal to 35. And 1.75 times negative R is minus 1.75 R, and that's equal to 41. And I'm just going to double check that. Another way to look at that is 1.75 times 10 is 17.5, double that is 35. And if you're not sure about these things, you can of course check it on a calculator. Now I'm going to simplify. I'm going to combine my two R terms together. 2.22 minus 1.75 is 0.22 plus 0.25 is 0.47. So I end up with 0.47 R plus 35 is equal to 41. 0.47 R is equal to 41 minus 35 is equal to 6. And for this one, I'm going to go off screen because 6 divided by 0.47 is not one that I'm going to hazard in my head. And I end up with, and I'm just going to double check everything that I've done up until this point. So make sure that I'm dealing with correct values. And so now I'm going to divide both sides by 0.47 divided by 0.47, and I end up with R is equal to now this one, if I've done everything correctly, is going to work out to be a decimal. I'm going to have to actually do an approximation here. So I end up with R is equal to approximately 12.76 6. That's plenty of precision for what we're doing here. So R is approximately equal to 12.766. And then from that, I look back. How am I going to use this value to find P? Well, equation number 3, so I'm going to sub R into equation number 3, because equation 3 is already written. P equals 20 minus, but instead of R, I'm going to replace it with 12.766. And this is approximate now. As soon as I put an approximate value into my equation, my whole equation becomes approximate. And so P is equal to 20 minus my answer, and that gives me 7.234, and that is also approximate. So that's I think this, were we talking about mass? Yes, that's the mass of the raisins, 12.766. This is the mass of the peanuts, 7.234. Therefore, and now in your concluding statement, this is where you can choose if you decide to reduce. If you want to round a little bit more, you can. So I'm just going to round this to 1 decimal place, unless it's specified here. How much of each type? It really depends on what kind of scales they might have. So if this is in kilograms, would they have scales that would read down to 1 gram? Actually, you know what? A grocery store might have something like that. I don't know if I'd want to be the person to have to measure this out, but therefore the mass, actually, can we write this in a slightly more condensed way? Sure we can. We could say that we want I'm going to write that as just 12.8 kilograms of raisins and 7.2 kilograms of peanuts. And I'm just going to take one last check, make sure I'm answering this question correctly. Total of 20 kilograms to sell for $41. Okay, so that's it for our tutorial. Let me just double check. I think that's it for my examples. It is just some homework questions from that point on.